Here we have infinitely many sets an, where n is a natural number, any natural number, and these sets are defined as containing all the multiples, all the integer multiples of n, right? Actually, these sets here are normally denoted in the literature just like this. These are the multiples of the integer multiples of n, right? But anyway, we're going to denote it an because that's the notation we're using here. And these are not the sets we're going to be concerned with. The set we want to analyze is this set G, whose elements are precisely these sets here. And the operation we're going to consider on this set is the intersection of sets, right? We want to know what is the structure in this set, right? What is the structure defined by this operation? Okay, so let me begin by trying to figure out what is the intersection of two arbitrary sets like this, right? So where n and m are two arbitrary natural numbers, right? So clearly here, the set, which is the intersection of these two, will contain all numbers which are at the same time a multiple of n and a multiple of m, right? Because it's the intersection of both, right? So it contains all the multiples of both. And clearly, this can be described as the set containing all the multiples of the least common multiple of these two numbers. Remember, this is the notation for the least common multiple of two numbers, right? Least common multiple. So just as an example, if I write a2 intersection a3, well, the least common multiple is 6, so this set is a6. Similarly, if we have a4 and a3, well, the least common multiple of these two is 12, so this is a12. Or if we have a4 and a6, again, the least common multiple of these two is a12, right? Okay, already this example that we have described here tells us that this cannot be a group. Because remember, if you have a group, the product of two different elements can never produce the same element, right? Sorry, the product of an element with two different elements, right, here, so a4 is multiplied by a3 here and by a6 here, cannot produce the same element, right? We know that for a fact. Probably what is going to fail is the inverse here, because if there is an inverse, this cannot happen, right? Okay, so let's see anyway what properties of the group this set has and which properties it doesn't. So the first one is, of course, this is it's a closed operation on the set, right? Because if you make the intersection of two sets, you produce another set of the same set G, right? So that's okay. Now it's associative because G1 is okay, it's associative. Because so is the intersection of sets, right? So it's an associative operation, and also is G4 is commutative, right? Commutative. So whatever it is abelian, okay? So at least it's a semi-group, right? Because it's associative, and the fact that it's commutative makes it abelian. Now, is there any neutral? Well, the neutral is, I think it's clear, it's just because of this, it's just one, a1, right? If you make the intersection of an with a1 is just set, right? There's another way of writing set. It's all the integers. It's all the integer multiples of 1. That means all the integers, right? So if you make an intersection of this with all the integers, of course, produces just an, right? Whatever n is. So this is the neutral. Okay? So it's an abelian monoid for the time being, right? And now we have to figure out whether G3 holds or not, which we already guess it won't hold because of this that we have found here, right? And actually that's the case, right? Because if we have n and n is larger than 1, for instance, and then we need to find am such that this produces a1, well, that is impossible, because what this produces is just a and m, and the least common multiple, of n and m is of course larger than or equal to n and m themselves. And since n is larger than 1, this can never be, this is of course larger than 1. So this can never be 1. So that this is impossible. And that's what the property that is missing. So associativity is okay, neutral element is okay, it's also commutative, but this property here fails. So what we have here is just an abelian monoid. So G is an abelian monoid.